Hello everybody and welcome to Mathematics with Combest, and today we're going to be slicing through some paradoxes here with section 1.4 in Patrick's Suppes Axiomatic set theory. So we're going to be going over section 1.4, which is on more paradoxes, and before we get into the part of all of these paradoxes which I'm going to mention, let's talk about the general forms in which paradoxes emerge. This was actually come up with a guy by the name of F.P. Ramsey in 1926. This classification of paradoxes into two classes explicitly. So you have in one class the logical or mathematical paradoxes. And then in the other set, the other class here, you have the linguistic or semantical ones. Okay, so what do each of these mean? The logical or mathematical paradoxes, those ones are from purely mathematical constructs. So like, we're going to get into some of these here pretty soon. So here are some examples. This being Cantor's paradox, Russell's paradox, and Burali-Forti paradox. That's a name, not a number, by the way. 40. Forte. Okay. Louder. Let's see here. The linguistic or semantical ones. So these are like direct consideration. Of the language which we use to talk about math or logic. So we have here two different types of paradoxes, mathematical and semantical, and that's pretty much it for classifying for our purposes. So let's get into one of the first mathematical ones that we have here. Right, so this is Burali-Forti's paradox, published in 1897. So, the idea behind this is that there is a greatest ordinal. So every well-ordered set has an ordinal number. Well, what do I mean by ordinal number? Well, that's just first, second, third, etc. So the set of all ordinals is well ordered. Once the set of all ordinal numbers has an ordinal number. Let's say this. Let's say that's O. Let's say this ordinal number that it has is O. So that's the statement for now. So the set of all ordinals is well ordered once the set of all ordinal numbers has an ordinal number. And can we say that this is the greatest ordinal number? Well, let's write that down. The set of all ordinals up to and including any given ordinal is well ordered. And thus has an ordinal number. Which exceeds the given ordinal by 1. There we go. So what does this mean? So we have that the set of all ordinals is well ordered. Once the set of all ordinal numbers has an ordinal number, let's say this is O, the set of all ordinals up to and including any given ordinal is well ordered and thus has an ordinal number which exceeds the given ordinal by 1. Well, with that in mind, let's look at the consequences of all these statements. So we have that the set of all ordinals including O as the ordinal number O plus 1, which is greater than O. Therefore, O is not the ordinal number of all ordinals. So we have that in a statement. This thing is the ordinal number of all ordinal numbers, but it's not, because there is in fact, by our reasoning, an ordinal number O plus 1. So it can't be, even though it's supposed to be. So we have this sort of paradox. We have this paradox right here with Virali 40. So let's move right along then. Discussing some similarities and what we can take from this as it relates to set theory. One of the things we can learn from this actually is that, well, you can derive. So paradoxes, from what I know, they're largely context dependent, and so what that means is you can either restrict or enlarge the context of what you're describing to mitigate the extent or the existence of a paradox. So, for example, J.B. Rosser in 1942, he derived this paradox in the system of Quinn. So whenever I say the system of Quinn, what I'm talking about is like the set theory of Quinn. There's all these sorts of set theories, right? And so you can derive a paradox in one domain of thought. So let's say like you can get an error by doing something in Mac OS, let's say, but you can't get it if you do the same exact thing in Windows OS. So it's like that. Like we have set theory sort of acting as the operating system behind these. We have different sorts of set theories acting as an operating system around this sort of thought. And it's clear that no direct derivation of Russell's paradox is possible in Quinn's system. Yeah, so that's interesting. So some systems may be prone to having paradoxes that don't exist, well, in other systems, but not be prone to having other sorts of paradoxes. So the takeaway here is like the system of thought that you're using for set theory, whether it's be Zermelo, Frankel, or Quinn, or Newman, a whole bunch of other names that I'm forgetting at the moment. Each of those systems has their own sort of weaknesses, let's say, weaknesses and strengths in regard to paradox. And so you can sort of, it's like you wouldn't choose Mac OS, let's say, for its customizability, right? But you would choose it if you wanted a closed system, a really closed system that wasn't prone to getting viruses and whatnot. But if you wanted something that was a bit more free, you'd choose Windows OS, right? If you wanted something a bit more freer, you know, you'd choose Linux OS for your computer. It's sort of the same thing going on here. This is an operating system. Think of it like an operating system behind these foundational roots of mathematics in this area. So with that in mind, let's go and slice through. Let's go ahead and slice through another paradox here. So let's go to Cantor's paradox. It's very similar. Cantor's paradox of the greatest cardinal number. You know, I even made it a point in my head to point out, oh, this is different because it's cardinal. Nope, it's all ordinal numbers. Yes, so, of the greatest, it's the greatest cardinal number that's ever been. So this was actually found in 1899, but published in 1932. So consider the cardinal number n of the set S of all sets. On the one hand, it's clear that a number n is the greatest possible cardinal. But consider this. But consider the set of all subsets. Of S and its cardinal P. So this is the set of all subsets This is the set of all subsets, so it's a power set, right? And its cardinal is P. And by definition, you know, we have, by standard theorem and definition, we have that, and this is just intuitive set theory, naive set theory. P must be greater than N. So this is a contradiction. So it's like there's this greatest cardinal number. You can find it. It's this number N. It's the greatest possible cardinal of all the sets. But then we take the set of all the subsets of that, and it's like, oh wait, it has to be greater. So you could do this on and on and on. What you get is this paradox. And an important thing to note here is that now we've sliced through this paradox here. Actually, you know what? Since we've sliced through this paradox in terms of describing it, let's go ahead and... There we go. There we go. Right through that paradox. And I wonder if there's ever a comic where the Wolverine does this to erase things from a board. It's pretty nice. There we go. Rah! There we go. Ah, falling down. Okay. It's not as quite good job as I wanted to. But, okay. So, these paradoxes they can't occur in when the okay, so these paradoxes, like I was saying about different sorts of set theories acting as like operating systems to a computer, these paradoxes can't occur when we have the axiom for construction. Let's say the axiom for constructing sets is Zermelo's axiom schema of separation, like we discussed earlier. Of separation. As the existence of the set of all sets or the set of all ordinal numbers, etc. Cannot be established. So we can't even set up that these sets that we were discussing in these paradoxes exist in Zermelo-Fraenkel set theory, because Zermelo-Fraenkel set theory, the way that it deals with these paradoxes is that it changes what it means to be well, what it means to be a set, right? And so it doesn't change the universes of each of the sets so much as the sets themselves. So Grothendieck universes, if you're familiar with Grothendieck universes, they actually change like what exactly a set is dealing with sort of thing, versus like Zermelo-Fraenkel changes what it means for a set to be a set in and of itself. So we have the Zermelo-Fraenkel system not allowing for these paradoxes to occur. Moving right along here, let's discuss an ancient paradox. You know this is ancient because, let's look at the name here. Whose paradox is this? It's Epimenides' paradox. No modern person these days is named Epimenides. Maybe. So, Epimenides' paradox of the liar. And some of you may have heard of this before. This is actually the oldest semantical paradox we have on record. As far as I'm aware, and as far as Patrick Suppes is aware in this book, oldest semantical paradox. Recorded. So, person A says, I am lying. Now, this is actually quite obvious why it's a paradox. So if the statement is true, then he is lying, right? Then he is lying, and the statement is false. If it's true, it's false. If it's false, it's true. Sounds like modern-day politics. So, if the statement is false, then he's not lying. And the statement is true. Other examples of this. So, as far as the format of this paradox is concerned, it's quite versatile. So what I mean by that is, let's say you have different scenarios, right? Like the only sentence written right in these quotations is false. So you can see the problem there. The only sentence written right in these quotations is false. Well, I mean, if it's false, then it's true, and if it's true, then it's false. And so you have another example right there. Another example, which I find kind of comical, in a dark sort of way, is there's this crocodile, and he's stolen a child. And he says to the father, the crocodile, right, the croc, which, by the way, crocs, like, this is the weirdest thing. Crocodiles, they have, no, they're the ones with the pointy snouts. And alligators are the one with the rounded ones. So alligators have the rounded. It's the weirdest thing because you think A and then you think this should match up, but it doesn't. It's a cruel trick of naming nature. Okay, so the croc says, I will return the child. I will return the child if you guess correctly. Whether or not I will return him. So the croc says, I will return the child if you can guess correctly whether or not I will return him. So you can sort of see trouble that's coming about here in terms of paradox. So the father replies. He says, you will not return the child. So what's the crocodile going to do, right? So you're not going to return the child. Okay, you're correct. Then he doesn't. But in which case you have to give back the child, in which case you're wrong. You know, at this point the crocodile would have probably just eaten the child, but it's a magic, smart, sophisticated crocodile. Well, smart enough to talk, but not smart enough to sort of figure out something that doesn't wind him up in this situation. So basically, the dad and the crocodile are at a standstill for all of time continuum. So yeah, let's move on to another semantical paradox. These are all the versions of Epimenides' paradox of the liar. Now, let's move on to one of the first modern published ones, which is Richard's paradox. Get a sip of coffee. Check if that's recording. Wouldn't want that to be something. So, first we need some semantics. Funnily enough, we need some semantics here. So by expression of the English language. Oh man, I forgot to do the thing. It looks like we sliced through describing Epimenides' paradox there. I have to do it every single time, otherwise it's a joke. You know, you beat a dead horse, and once you started, you can't stop. Otherwise you admit that the joke is unfunny, and you can't do that, so you have to double down. So, Richard's paradox, 1905, by an expression of the English language, let us mean any finite sequence. This one's kind of a cheat semantical because it uses something which is very similar to a mathematical paradox, and which I'll show you here in a moment. Finite sequence of the 26 letters, a comma, period, and a blank space. So it's a finite sequence of any of these 29 symbols. You see, like sequence, you know, that's a very mathy term, right? And so finite, very mathy term. So it's kind of a tiptoe around. It's a construction. It's a semantical paradox that's mathematically constructed, I'll say. So these are the conditions here. Now, to show what that actually means for okay, so let's order the expressions. According to the total number of symbols and lexicographically. Within each total number, we have the sequence looking like this. A, B, dot, 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 A, B, dot, 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 A. So you can see where the pattern's going here. So let's strike out those expressions. Do not define real numbers. And let E be the remaining subsequence. So we're going to strike out those expressions which do not define real numbers, and let E be the remaining subsequence. I spelled strike wrong, I just noticed that. Oh well. Striker! Okay. So, defining a real number n with respect to E we have that the real number whose whole part is 0 and whose nth decimal is p, is p plus 1 if the nth decimal of the real number defined by the let's see here, whose nth decimal is p plus 1 if the nth decimal of the real number defined by the nth member of E is P, and P is neither eight nor 9, and is simply 1 if this nth decimal is 1 or 9. Okay, so what does this mean, right? Defining a real number n with respect to E, a real number whose whole part is 0 and whose nth decimal is p plus 1 if the nth decimal of the real number defined by the nth number of E is p, and p is neither 8 or 9, and is simply 1 if this nth decimal is 8 or 9. So what this means as a conclusion here is that, well, it's like I was sort of saying earlier, that this is by construction a paradox that is laid on the grounds of mathematical thought. So, by construction, n is not a member of E. Since it differs from every real number, E in at least one decimal place. But n is defined by a finite expression. Whence it's supposed to be an E. Basically, this is reminiscent of the way Cantor proved that the uncountability of the real numbers, but in this case it's it's different because it involves letters, and so therefore it's symmetrical. By construction, n is not a member of E, since it differs, if you remember earlier, from every real number E in at least one decimal place, but n is defined by a finite expression once it is in E. So we have there a contradiction, a paradox with itself here, because let's say, you know, you're saying that, well, I mean, you get it at this point, because n's not supposed to be a member, but we defined it to be a member, right? And so therein lies the crux of this semantical paradox. So let's move right along to another semantical paradox now that we've sliced through Richard's paradox here. Ha! Let me just stab this eraser. There we go. Now that we've sliced through this paradox, we can erase it here from the board. And it shall never return. We just... There we go. This is actually kind of fun. You know, I can see why it hurts Wolverine, because these things are kind of hurting my knuckles right about now. These got like infinite healing. I don't have that, and so these things are just sort of stabbing into my knuckles here. Just not that extreme. It's just gotta stop whining. There we go. So moving right along here, let's get to one of the final few. Grelling-Nelson paradox. So this one is actually kind of clever. I actually like this one. So a predicate is called heterological if the sentence describing it, well, the sentence ascribing the predicate expressed by the predicate is false. Heterological. So, an example of this, speak of this more concretely here. Predicate red is heterological since the sentence predicate red is red is false. So you see what I mean by heterological there. So the predicate red is heterological since a sentence, the predicate red is false. Right. So here we run into the paradox of the word itself, heterological itself. So, and just erase this real quick. So is the predicate heterological. Itself heterological. Because if it is, we infer it's not, right? So if it is, it's not. Yay! Does that make sense? And if it's not, we infer it is. And so it's like heterological is heterological. It's like, is that true? Hey. So you run into a bit of a paradox here. And so we've sliced right through that paradox, and so it's time to erase it from the board here. This may not be the most effective means of erasing this, but I started this and I'm finishing it. There we go. So, going back to what we were talking about, what's the main theme here, right? If we could have a main theme in discussing these paradoxes, it's like if you restrict something, or if you restrict the context, or you restrict the language itself, you avoid the problem of paradoxes in a system. Because if you arrange the language in such a way that a paradox cannot be described, then you sort of, in a way, get rid of the paradoxes. So Zermelo, he specifically introduced this, right? And this is what a lot of people have a problem with Zermelo, Frankel set theory is like it's too rigorous, is their notion. But the reason why Zermelo specifically introduced his notion of definiteness and why he does a whole lot of other things to add to that claim of rigor is so let me just write this down. So he introduced this axiom schema of definiteness. In the axiom schema of separation. To prevent construction of semantical paradoxes. So in a way, we're kind of 1984ing all this stuff. Okay. So, before we finish off this chapter here, this introductory chapter, let's just go about and speak to certain terms here to just nail in place exactly what we're talking about here and how exactly all of this is important. So, we have that in object language. It's the language in which we talk about sites. And then we have the meta language. So that's language in which we talk about the object language. So we have the object language, language in which we talk about sets, meta language, language in which we talk about the object language. Here's something to remember. Paradoxes, if you want one phrase to take away from this, paradoxes are avoided by restricting the richness of our language. There's this sacrifice made here. You have all this pretty stuff, but all this pretty stuff has fluff, and that fluff mixes together in such a way that produces things that are logically incoherent. So paradoxes are avoided by restricting the richness of our language. That's the takeaway. So we have to have these restrictions because a complete and exact formalization of the object language is necessary for proving metamathematical facts about Zermelo-Fraenkel set theory. So metamathematical facts are they're facts about the object languages, the object language. So, an example of this complete and exact formulation that we can only obtain by restricting the language, by restricting the richness of the language here. Is the axiom schema of separation cannot be replaced by a finite number of axioms in the object language. Right. So, how exactly do these different sort of restrictions shape Zermelo-Fraenkel set theory and other sorts of set theory? Well, the different sort of restrictions, they get different sorts of set theory. So, the von Neumann Bernays set theory is another method of approach. And there are two essential differences in between von Neumann-Bernays set theory and Zermelo-Fraenkel set theory. Two essential differences. One, it may be finitely axiomatized. So, what I mean by this is, in von Neumann-Bernays set theory, no axiom schema of construction like that of separation is required. But instead, we have a finite number. Of specific set and class constructions. So, difference number one. In von Neumann-Bernays set theory, we have that no axiom schema of construction like that of separation is required, but instead a finite number of specific set and class constructions. Class constructions. Two, the set is a class, but class not necessarily a set. So classes are not sets. Not sets are proper classes. So what I mean by that is they are not members of any other class. Any other class. So this is the second difference here. The set is a class, but class is not necessarily set. In von Neumann-Bernays Go set theory, we have these things called classes, and that's how you go around things like Russell's paradox, because you don't have the set of all sets, because instead you have these notions of classes, which eliminate the idea of having a set of all sets. Because you have like a class that can contain all the sets, but that's not a set, that's a class. Different thing. Okay. So it's like the class of all ordinals and the class of all sets, those both exist, but they're not proper classes, right? And so the Burali, Forty, and Cantor paradoxes cannot be constructed, as they require the classes to be members of other classes, right? I mentioned Russell's paradox earlier. You don't have this sort of deal here going on, because proper classes can't contain other classes. Boom. Done. Out of the way. And so we reach the end of this chapter. Chapter 1. Let's just sort of preview where we're going here. 1.5. So we're going to discuss the axiomatic existentiality of, then the axiom schema of separation a bit more, union axiom, pairing axiom, sum axiom, power set axiom. We're going to get more in depth into these things here in the next few episodes. So for now, thanks for watching Mathematics with Combus, and we'll see you in the next episode.